So now I'm going to bring you on to something that I'm going to say is a slightly different perspective on the way that we've been conducting tests. Okay, so the scenario is that in many applications we simply say that we collect enough data and then we appeal to the central limit theorem and away we go with our t-tests and our ANOVA tests and these kinds of setups. But it's not always the case that it's possible to do that. For example, we might have a classification system that doesn't readily lend itself to that kind of analysis. We might have letter grades on something, or classification system that is ABCD, something like that. We might not have much data. It might be something that we're looking at is quite rare, so it might be quite difficult to get enough observations to allow us to make some sensible statements or allow us to use the methods that we've been looking at. So we might have data that are not normally distributed and we might have a small sample, in which case we might need to know about some different techniques. Now these are things that we see in the natural sciences. You see them less in many business scenarios or many other applications where they don't run into the problem of small samples very often. But because in the natural sciences we're often maybe out in the field trying to sample things where data collection is very expensive or the thing we're looking for is rare, so regardless of how much time we spend, we're only going to get small samples. So we introduce another thing which are called non-parametric methods. So the setup that we have here is that pretty much for every parametric method, so the parametric methods that we've been covering are the ANOVA and the t-test, and later on we'll also cover regression. So these methods are called parametric tests. For all of these, there is an equivalent non-parametric test. So the issue with parametric tests is that some of the assumptions that we need to make them valid are not always available to us. So if we have a small sample, we need that sample to be normal, come from a normal distribution, or if it doesn't come from a normal distribution, we need a large sample, okay? So if we don't have those conditions met, what are we going to do? Our approach of using t-tests and ANOVA is not going to be such a great idea. What you should be aware of, if the assumptions of the model are correct, then the parametric methods are the best methods to use. So if we do have a large sample, or we can be relatively certain from a range of evidence that our small sample comes from an approximately normal distribution, then it will be still best to go with the ANOVA and the t-test. But if we have small samples and we don't know that they come from a normal distribution, then we're going to be thinking that it might be an idea to use one of these non-parametric tests. Or we just have data that are classified in a way that doesn't lend itself to the kinds of analysis. They're just not numeric grades. So we don't have a clear ordinal relationship between what HDD or the quality of the stream means. Okay, so non-parametric methods are always going to be valid. So if we could, even when we can conduct parametric analysis with safety because the assumptions hold, we could also conduct non-parametric analysis of those same data sets. The reason we wouldn't do that is because that if the assumptions are true, parametric methods have greater ability to detect differences if there really are differences than non-parametric methods. So non-parametric methods are valid over a wider range of circumstances, but if the assumptions of parametric methods hold, the parametric methods have more power than the non-parametric methods. So if it's valid to use parametric methods, if it's valid to conduct a standard ANOVA or t-test, then that's the path that we want to go down. Only if the assumptions don't hold do we want to look at these other methods. Now the way that they work, well firstly maybe let's get our head around the terminology. So basic setup is a little bit of a problem because the language is not as consistent as it is for our t-test scenario. So we have a couple of examples, that we can run through here. So we have a Mann-Whitney test. If you look up this in the literature, why does it keep doing that? That's the equivalent of a 2-sample t-test. And the previous setup, if you were looking for a single sample t-test, that would be called a Wilcoxon test. Now, both the Mann-Whitney test and the Wilcoxon test are implemented in R as a Wilcox dot test. So there's a little bit of confusion in the language. So if you go and look up, the equivalent of a t-test for in the non-parametric world, some literature will say, oh, this is a Mann-Whitney test. Others will say this is a Wilcoxon test. So not quite as consistent in the literature, so it can be a little bit confusing. A little bit easier for the ANOVA equivalent, the Kruskal-Wallis test, and this is the notation that's used in R is Kruskal-Wallis. So we have some consistency there. So if we want to conduct any type of t-test equivalent, so when we want to do this, when we have small samples where we're worried that the sample data doesn't come from a normal population, and we have small data, we're worried about the assumptions of the t-test being valid, so we might apply a non-parametric test, okay? The command for generating those tests is the Wilcox test in R. And if we want to do the equivalent of an ANOVA, because we have multiple groups, we would have the Kruskal-Wallis. And similarly, when we want to do pairwise comparisons following the ANOVA, there is the same as a pairwise test that imposes the same adjustment for multiple comparisons. Now, the setup for these tests is that they work on the ranks of the data. Okay, so they don't work on the actual numerical values themselves, but they work on the ranks of the data. So we're going to look at what that is. And that also means for us that we don't have any variance ratio kind of tests because the rank order is the same. All right, the rank order is always evenly spacing. By rank order, I mean, it'll be clear when I show you some examples. Now, for the null hypothesis, there are many ways of framing them. But the most important thing to get out of this is that we don't generally say means. You can say the mean of the ranks. Under certain conditions, you'll see the null and alternative hypothesis specified in terms of medians, which under certain assumptions is true. A more general statement, or the most general statement that you see for the null hypothesis for these kinds of tests is that group A weight is the same as group B weight. Okay, so it's nothing about the mean or the median, could be any reason for a difference, but it's just that they're the same. So hind legs equal to forelegs, or is the same. All right, so we don't say mean. All right, so we're going to use probably these general statements about a null hypothesis. It'll make sense once we get into these. So let's look at the first setup, which is the Mann-Whitney test. Okay, what are we going to be doing? We want to compare two samples and understand if they're different. I've said that the test works on the rank of the data. What does that mean? It means that you rank the data from highest to lowest, and then you give those positions a value or a rank order. There is a test statistic that gets calculated, but the way to think about this is that if the data clusters in terms of all of one group in the rank order is at one end of the distribution, that's evidence of differences. And I think that this will make it will be easier if we look at some examples here. So here are my two groups. I've got two small samples, and say, for example, I want to compare these two groups, and I don't think that these samples come from a normal distribution. So I'm worried that the assumptions for my t-test. Now, if I'd had, a large sample, I wouldn't care. So if I have a large sample, which, maybe 20 observations, I really wouldn't worry about what the population shape was. But because I've got such small samples, I'm a little bit worried about the population shape. Now, when we had parametric tests, we always had a plot. So when we're going to have non-parametric tests, we're also going to have a plot. Now, this is where I'm going to introduce you to, I guess, a little bit of a balance between what's practical and what's, technically correct. With non-parametric plots, it's not usually that common to see box plots. Okay, it's usual to see stacked histograms. All right. Now, the problem with that is that it's quite complicated to make a stacked histogram that looks nice. So if we wanted to do that, It is possible to do that, but you have to start using some add-ons to R, and the particular one that works well with this is what's called the lattice package, and I can show you what a stacked histogram looks like. We're going to just stick with a box plot. So it's really easy for us. We know that for any test that we want to conduct, we're going to have a plot, that's central to our argument. In this case, we're going to just keep on going with box plots. Okay, so if I was to, prepare a stacked histogram, this would be the kind of thing that you would do for a non-parametric test. This is what most people would do. We're going to just stick with saying, well, we're comparing two groups. Whenever we compare two groups, we're going to stick with a box plot. And this tells us pretty much the same story, that we're looking like our male data is a little bit higher than the females. Okay, so let's get back into our formal testing approach. So we need to specify our null. Male tuner length is the same as female tuner length. So I'm not saying anything about the means, just general statements, very vague sort of null and alternates. The alternate, male tuner length, is not the same as female tuner length. Set the alpha level the same. Now, there are test statistics, just like we had formally what goes on is there's a calculation of a U statistic, just like with a t-test, formally what happens is there's a calculation of the t statistic. We're going to, in practice, apply p-value decision rule, which is if the p-value is less than 0.05 when we conduct this test, we're going to reject the null that the male tuner length and the female tuner length is the same. If the p-value is above 0.05, we're going to conclude do not reject the null. All right, so let's walk through the test mechanics here. So we've got my data is ordered. Okay, so here I've got my male data and my female data. And what I want to do is I want to identify the rank order of them. So let's have a look at what I've got here. So can you see how I'm working here? I've said the highest observation in my data across both sets is 193. So the male gets a rank of 1. So I replace the value of 193 with the rank of 1. The next highest observation in the data, 88, that gets a rank of 2. 83 gets a rank of 3, 4, 80. Now, after 80, 78, that's the 6th in order. So the rank in the pooled data set between these two of females is 6. And then I jump to 75, so 7. So this is the 7th in the order of the two sets. So that goes to males. Then 173 is the next one. So that goes, so 8, rank 8 goes to the females. And then you can see 9 goes back to the males, 10, 11, 12 are the females. So the 3, so you can see that we're starting to get some clustering here, that this tail of observations are the females and the start ones are the males. So when the rank order is set up like this, that they cluster, the males are clustered at this end and the females are clustered at this end, that's evidence that the samples are different. So my test though, my test works on this. These are the ranks, okay? So the rank of the data, not the raw data. So the difference between the non-parametric test and the parametric test, if we conducted a t-test, we would be using the raw data, this data here and this data here, and we'd be calculating the differences in the means. For the non-parametric tests, we don't use the raw data. We're using the ranks, okay? So these are the rank orders of our test. And you can see that this is called the rank sum. If I add up all the values for the males, I get 31. If I add up all the values for the females, I get 47. Okay, but we also know that these two sample sizes are different as well. One is 7 and one is 5. So we need to factor that into our test statistic as well. Now the formulas for the test statistic are given here. You usually calculate them by, you calculate both, and you can see it depends on the sample size, and it depends, that's picking that up here, and it's looking at the differences in the rank order here, and it plays out the same way here, looking at the differences. So it's looking at the number of observations and the sum of the ranks, okay? We do the same for both. So let's just have a look at what happens if you plug those values in. So this is the test statistic. Remember, the t statistic, there's a formula. This is the formula for the test in a non-parametric test. You know, just like the t-test, we're going to rely on R to do the calculations for us. We're just seeing how the calculations work here. So I plug all these values in, ... work through the formula again. There's no fixed reason why I should have picked one, ordered these groups as, 1 and 2. So we calculate both tests and I get a value of 3. All right. And so then what I do is I look up the critical value in my statistics table. I have a book which has hundreds of pages of these things, which is what we used to do in the past. I see that the critical U value in my statistics textbook. So when I get out my test statistic, it would be, this is a two-sided test for an alpha of 0.05. I have 5 observations in group 1 and I have 7 observations in group 2. If my critical value, says my critical value is 5, my U value less than 5 would mean that we would reject the null. Okay, so the way that this test is set up is that it works the opposite way to a t-test. But that's all hidden in the background, okay? So we would have all of this stuff set up, right? I've also got to guess a notation that, again, these, the way that these tests have been explained in the past, there's different ways that statistics books work. So that there is a critical value, could be above or below. We're not worried because we're worried about this line. How do we implement the test in R? Now, the one thing that I have to give you a warning about is that R can give you warnings. So a warning in R is nothing different from a warning. It doesn't say that something is wrong. It says you might be aware of this. And whenever you get a tie in the rank, so that means that you get 2 values that have the same numeric value, R lets you know about that. You can hide that, but I'm not, it's a bit hard for me to do the settings on your computer to hide that. So when you get a warning for this test, you don't worry about it. All right. What do we need to know? We need to know how to implement the test. So let's have a look at how we implement the test. Okay. Really straightforward, just like a t-test, except with tuner data, implement the Wilcox test. Length, that's my measurements. Type, they're my males and females. So I just get my test. It gives me my test statistics. So you can see that it gives me my critical value there. That's the one that I calculated by hand. We just look at this guy here, which is our p-value, which is lower than 0.05. So we would reject the null of equal group variances. Okay, so what did I want to show you here about also the warnings? So what I've got here is just an example to show you what would happen. So if you had values that were the same, so if you had 78, 78, 78, the way that the test works is it would take the average of the rank of 5, 6, and 7, because they're the order that those locations put them in, and it puts a 6 in for all of those values. So when you get a scenario like this, R gives you a warning that says there's a tied ranks. It doesn't matter from us, from our perspective, that's fine. Our interpretation of the p-value is left unchanged. And that's an opportune time for a break.